All right, so let's start with the next section of this chapter on DC to DC converters. In the last section, part 5a, we discussed about some basic principles and basic introduction on DC to DC converters. And we also started talking about different types of converters. We'll summarize linear regulator, which we discussed in the last section. But mainly, the focus of this section will be on switched converters, and then a type of switched converters, which is buck converter. This buck converter is simply a step-down converter. And after completion of this buck converter, we will start with the boost converter, which is a step-up converter. And then later on, we'll discuss about the combination of these two converters, a converter which can step up as well as step down using the same circuit. So the focus of this section will be switched converters. But just to summarize or recap from the last section, part 5a, so that we can have a smooth transition from linear regulators to the switched converters or switched regulators. In linear regulator, as we discussed, that using a simple circuit, we discussed a source connected to the load through a switch. In this case, it's a bipolar junction transistor used as a switch. And its equivalent circuit, we can see here that this transistor can be represented by a variable resistor. So we are already aware of this equivalent model, which we can easily relate with the voltage divider circuit. So using this voltage divider circuit, we can easily find out the voltage at the load, which is R2, using voltage division principle. And then similarly, we can find out the ratio of output and input, also called efficiency. So, but what is the main problem associated with this type of linear regulator? As we can see from here, before going into the problem, we can see from here that it's simply a voltage divider. And in voltage divider, we know that this input voltage is divided into two resistances, R1 and R2, depending upon the values of these resistances. So at the load, V out, we always have less than V input because of the voltage division rule. So linear regulator, from here we can see that using this equivalent model, we can see that it is a step down regulator because the output will always be less than the input because of the resistance in between load and the source. So linear regulator is always a step down regulator. Now, the main problem associated with this regulator is that this transistor operates in linear mode. So that's why we call it a linear regulator. So what's the problem associated with this particular circuit? Thing is that the output power is normally far less compared to the input power. It means due to the operation of this transistor in linear region or inactive region, we can have a lot of power losses in between. And I will go through this one by one, that the load current, as we already discussed in section 5a, that the load current is controlled by the transistor, because from here in the active region, we can easily control the current levels over here in the active region or a linear region. So by adjusting any of the base currents over here, so here I've shown about 4 levels of base currents. So just by adjusting the transistor base current to any of these values, we can change the output current or the load current, which is collector current. Due to this operation of this transistor in linear region or active region, it is called a linear regulator. So due to this operation, a lot of power losses are incurred. So that's why this linear regulator is not an efficient circuit because of power losses. So we have to come up with an alternative which can give us a higher efficiency or an efficient design or an efficient regulator, where we can have lowest power loss or as low as possible to increase the efficiency. So let's start with the switched regulator. So now this switched regulator, we assume this switch to be an ideal switch for academic purposes. In practice, it's not an ideal switch. We have already discussed about ideal and practical aspects of switches in part 3 of this course. So assuming an ideal switch, we can see the difference between the linear regulator and the switched regulator. So let's start with the switched regulator. So looking at this circuit, when the switch is open, means when this switch is off, no current flows through it, the transistor is off, so the load is now disconnected from the supply, so no current flowing. Now when the switch is closed, that means the transistor is now turned on. And now the load gets connected to the voltage supply over here. So now the current starts to flow in the circuit. But at this moment, let's see how this switched regulator is better compared to linear regulator in terms of power losses. Later on, we'll do the principle of working in detail. So when now the switch is closed, means transistor is turned on, the current starts to flow. But assuming this as an ideal switch, no voltage drop will happen in this switch. So all the voltage as per the KVL, Kirchhoff's voltage law, if the voltage drop in this transistor is 0, so all the voltage in the input will reach at the output. So if we can easily relate this with the Ohm's law, we can find out that when the switch is off, no current flows. And we all already know that the formula of power is voltage multiplied by current. And when switch is off, current is 0, power is 0. V into 0 is 0. And when now the switch is closed, means the transistor is turned on, voltage across it is 0. We have a current flowing through it, but voltage is 0. Again, the power is 0. So it means that power loss in this switch is 0, no matter whether the switch is on or off. So all the power will be transferred to the load because of the power loss of 0 over here. So that means we can say that it has a 100% efficiency. So that's what the main concept of a switching regulator is. So we'll see that in more details in the coming slides, but that is the basic concept of a switching regulator. So just before we continue further, here I'm just mentioning a state of this switch as open, means off, or closed, which is on. So this switch is now working in two modes only, off mode and on mode. Off mode is called cutoff region, on is called saturation region. So this transistor is now working either in saturation or in cutoff region. So now we are not working in linear region. So that is the basic difference between linear regulator and a switched regulator. In linear regulator, we operate the switch in linear region, which always has a voltage drop and a current flowing through it. Always. So it always has a power loss. And if it always has a power loss, the output power is less compared to input. So the efficiency is very low, depending upon the power losses. So it can never have a 100% efficiency in linear regulator because of the operation in linear region. But in this case, when the switch is on, power is zero, ideally. When switch is off, power is zero, ideally. Power loss in switch. So the whole power reaches at the output. So it means output divided by input is 100%. So it means from now on, regarding this switched regulators, we'll be dealing in saturation region and the cutoff region. So any switch will be operated in cutoff or saturation. So this is the waveform. When the switch is on, we have this value Vs equal to 42 volts. When the switch is off, 0 volts. So when we have complete 42 volts at the output, this is an example for an automotive application. So this waveform shows the switch keeps on turning on and off in periodic nature. Periodically, it keeps on turning on and off depending upon the application. Only the width of this on pulse and the off pulse can be changed depending upon our application. So the width of this on pulse can be denoted by D multiplied by the time period. Total time period is T. And we know that time period T has positive half cycle as well as negative half cycle in terms of AC to DC converters. In this case, total time period is the time for turning on the switch and time for turning off the switch. So this is the total time period, as we have already discussed in part 3 of this course. So turn on time divided by the total time period is called duty cycle, which is denoted by D. This also we have discussed in part 3 of this course. Even the last 5A also we have discussed. So duty cycle is an important parameter in DC to DC converter. So we'll use that quite often. So before going into the buck converter, which is a switched converter, let's first refresh some of the basic concepts which we have already discussed in part 2 of this course regarding energy storage. We know that if we have an inductor in a circuit, this inductor stores energy. So this also we know how much energy it stores. So it means when the switch is on or it closes, this voltage supply over here starts to energize the inductor. So now the energy, this inductor starts to store the energy, which is equal to Li di by dt, di, because we are integrating this energy, which is equal to the inductance value multiplied by the current flowing through the inductor And how large is the inductor? This is shown by value L. And then we keep on integrating with the small deltas of current from 0 to the maximum value of current I, which comes out to be Li square by 2. And as I have already mentioned in previous lectures, that if we talk about resistance in a power electronic circuit, resistance always dissipates energy. So it's involved with dissipation, only losses. So it does not store anything, just dissipates. So this is, we can say, dissipation in terms of heat. This is a formula for heat. Okay, so inductor storing energy is important. Now capacitor, another storage element. So when the switch is closed, the capacitor starts to energize. It starts to store the charge, which is equal to the integral from 0 to maximum value V, capacitance, how much capacitance value it has, and how much voltage we apply here, which comes out to be CV square by 2. And in switch, we only have a loss of energy, which is equal to V square in switch divided by R, because all the switches have some resistance. But an ideal switch, like a MOSFET, as I discussed in previous lectures, that MOSFET has a very little losses. So that's why this MOSFET is preferred for low power loss or low power applications, because the power losses are very low in MOSFETs. And switches are close to ideal in all these semiconductor devices. So that's why the losses in switches are quite low, because we have seen in the previous slide that if we assume this as an ideal switch, during on condition, we have a 0 voltage, so power is 0, power loss is 0. During off condition, current is 0 in the switch, so again power loss is 0. So for the complete one time cycle, power loss is 0, so 100% efficiency. But if we consider this switch not to be ideal, still this is close to ideal. These values will be very low. So we can have quite good amount of efficiency. We will see later on as we proceed with the buck converters and all. Okay, again a revision from part 2, that in capacitors we see that this based on the voltage, energy and current. So this is the current over here in capacitance. So from here we can say the voltage dV by dt, the voltage cannot change instantaneously. So these concepts we will be using in converter circuits. So they tend to keep the voltage constant for a finite amount of time, because instantaneously they cannot change. So for some part of a time, they try to keep the voltage constant. And if we have an ideal capacitor, then it is as good as a constant voltage, so it's just like a battery. Regarding inductors, the other way around, they try to keep the current constant. Means initially they oppose the current, so they cannot allow the current to change instantaneously. So some finite time is required. So that concept also will be using in converters. Immediately, no flow of current can happen in inductors. No change of flow of current. So these, and again for ideal conductor, it has infinite inductance, so it can act as a constant current source. So based on the previous slide, I can just mention over here, let's say we have a switch, we have a load, just like the previous circuits we have seen. But now we have included a capacitor over here, just like we have seen in AC to DC converter or rectifier. We place a capacitor at the load in parallel to the load to remove the ripples. So let's say we have a capacitor over here, and it has already charged into some voltage, which is VDC2. So a capacitor is charged at some voltage. Now when the switch closes, means when we turn on the switch, immediately the current spikes take place. Immediately the current spike takes place and the switch can burn out, because capacitor does not allow the changes to happen instantaneously, but this voltage changes instantaneously. The voltage from this voltage source is applied instantaneously at this switch, but this capacitor voltage is not applied instantaneously at this switch. So due to this huge difference, we can have a spike, and that spike, if it goes beyond the rating of that switch, it can burn out the switch. So what is the remedy? That is the first remedy. So we can insert one inductor in between. And now thus this inductor will oppose the flow of the current, because when the switch turns on, means it closes, this voltage is applied instantaneously, so the current starts to flow instantaneously. But this inductor will oppose the flow of current. So it can save the switch from instantaneous current spike, as it was seen in that previous case, because inductor opposes the immediate flow of current. So that current spike can be opposed by the inductor. So this current can be saved. So all these current spikes are normally filtered by this inductor because it opposes it. So if it opposes it, it can throw these current spikes out. So we can save this current, this switch. But on the other hand, when the switch tries to open, because let's say when we want to turn off the switch, during turn on, this inductor comes to the rescue. We have seen that. But what happens when the switch now tries to open? So due to this huge L di by dt rate of change, due to the rate of change of current, huge voltage, and we know that because when switch opens, this switch becomes open circuit, and almost all the voltage in the circuit will be applied at the open circuit. So abrupt application of the huge voltage at this switch can burn out the switch due to the over voltage. In the first case, it was due to overcurrent, due to high current spikes. Now this can get damaged due to over voltages while turning off. So while turning on, it can be saved due to the presence of inductor. Again, I am repeating. But during turning off, due to over voltages, due to voltage spike, it can get damaged. So current spikes can be controlled by the inclusion of inductor during turn on, but during turn off, over voltage spikes can burn out this switch. So now we have to come for this remedy as well. So that remedy is the inclusion of freewheeling diode. So this freewheeling diode can save this switch when the switch tries to open. So now all these over voltages do not appear over here, because now the current will continue to flow here only. So now switch is out of the circuit. So all these over voltages are now already filtered out by this freewheeling diode. So we can save the switch by including inductor as well as freewheeling diode, so that the switch doesn't burn out. So these concepts will be used in DC to DC converters. And we have already used these concepts in AC to DC converters. Okay. Again, assuming this switch as a lossless, no losses. Practically, very low losses are existing in this practical circuits, but ideally, we assume zero losses. Now, we have already discussed continuous and discontinuous mode of conduction in AC to DC converters. But DC to DC converters, again, the concept is same, discontinuous current and continuous current. But here, the mode has different phases. Like in AC to DC converters, these converters, AC to DC converters, can work in discontinuous or in continuous modes, depending upon our requirement. Same is applicable in case of DC to DC converters. But the behavior is different. Here we work in phases. We'll discuss about these phases later on in buck converter. We'll start with buck converter. So we know that discontinuous mode, it derives its name from when during operation of the circuit, the inductor current flows intermittently. It does not flow continuously at some intervals. So this figure shows 4 phases of discontinuous operation. We'll see that. Now in discontinuous mode, as we know that the current goes to 0 for some part of the time period. So it means if current goes to 0 for some time period, it can save power. It can save losses. Because if current is 0, power is 0, power loss is 0. So it can save power losses. So that's why this discontinuous mode of conduction is normally used in smartphones, as I've already discussed in a previous chapter, or other portable devices where battery life is important. And in this one, the thing is that the variation in output power is met by using a controller. So controller can run a pulse frequency modulation or pulse width modulation. That also we'll discuss in next slides. So all these control methods are actually met by a controller. We'll see that what's inside the controller. So we need a controller to control this mode of conduction. Now continuous mode of conduction. And we know that the name continuous mode is derived from the operation of the circuit in continuous mode. So in this, the inductor current never goes to 0. It keeps on flowing continuously. So the application, as in discontinuous mode, it's normally used for low power applications or where power savings are required. In this case, we use this continuous mode of conduction in normal power operations, where savings in power are not critically important, like in microgrids, like in these power grids, electric trains. So we can use continuous mode of conduction. So in that case, we'll see that how these different parameters, the important factor like duty cycle, so normally used by the controller to keep the output voltage within defined limits. We'll see that. So again, in this case, we'll see that this controller needs to apply a control method which is called pulse width modulation. We'll see that pulse frequency modulation as well as pulse width modulation. This is all provided by the controller. The only difference over here is that it works in 2 phases, phi 1 and phi 2. Phi 3 and phi 4, which were available in discontinuous mode, are actually removed by the controller in a continuous mode. So now let's start with the buck converter. Buck converter is simply a step-down converter, like a linear regulator, where the output is always less than input. So linear regulator also always have an output which is less than input. But this buck converter is a switched converter. Step down and switched converter. So this is the basic circuit diagram of a buck converter. We have a DC input over here. We have a controller over here. Any amplifier can be used, or digital or analog controller. We'll see later on. So this is one switch which is called high SI, high. So high level switch. This is the low switch. So low switch means connected to the ground, low potential. High switch means connected to the battery, means positive terminal of the battery, or it is a high potential. So using two switches, we connect these with the inductor over here and then a capacitor in parallel to the load. And then this output at the load is now fed back to the controller. So in DC to DC converters, we normally feed back the output of the converter back into the controller, so that the controller can decide based on the feedback and the input whether to switch on or off these switches automatically based on the control algorithm inserted inside the controller. So for continuous mode, let's say we start with the continuous mode. For the continuous mode, we only have two phases. So this converter works in two phases only. So phi 3 and phi 4 are not there. So for discontinuous, we'll see later on where we'll be discussing with all the four phases. Let's start with the buck converter for continuous mode of operation. Okay, so this is a simplified diagram of a buck converter as we saw in the previous diagram. So instead of low switch, I have replaced that low switch with a diode, simple, so that it becomes simple in this first case. So the inductor was connected in between these two switches. So this inductor is connected between this switch and this switch. So this is a transistor switch, this is a diode switch, so that the things can be simplified. But in practice, we don't use diodes, we use transistors as switches because of their low losses. Diodes always have more losses compared to transistors. Okay, so let's start with the analysis with some assumptions. So let's say the circuit is operating in a steady state. We have already discussed about steady state condition and transient conditions in AC to DC converters. So if somebody wants to find out what is steady state or transient state, you can go back to that lecture and see the difference between our transient state and a steady state. So the circuit is already operating in steady state. Now the inductor current, as I just mentioned, we are assuming it is a continuous inductor current. So only phase 1 and phase 2 are applicable. Again, assuming that the capacitor is very large. And if the capacitor is very large, the output voltage is actually held constant. Means RC constant is large, so it can change very slow. So if it changes very slow, so it can be assumed as a constant. So this restriction will be relaxed later when we see the actual effects of finite capacitances. But to start with, we have to simplify the things. Okay, the switching period, as I mentioned, is time period T, which is the sum of on time plus off time. So the switch is closed, means turned on for time period dt, which is this one, and open or off for time period 1 minus d. So in this case, let's say 50% duty cycle, d means duty cycle. So let's say 50% duty cycle where on time and off time both are equal, which is 50%. So total time period is 100, on time is 50%, off time is also 50%. So we can call it a 50% duty cycle. This I've already explained in chapter 3, part 3 of this course. Now, taking example of 75% of duty cycle means 75% of the time, total time period T, this switch is on. And now only 25% of the time it is off. So value of D over here is 0.75. T on divided by T. So T on is 75, total T is 1, which is sum of T on and T off. It is so on time divided by T, which is 75 divided by 100, it is 0.75. So duty cycle of 25%, which means on time is now 25 and off time is 75. So D is equal to on time divided by T. That is basically the formula which I explained in previous lectures. So again, you have to remember it. So T on divided by T is duty cycle, which is 25%. Okay, so we have to analyze this converter in two stages. One is when the switch is closed, or when the switch is on, or when the switch is open. So now when the high switch is on, this battery is now connected to the load through this switch, and the inductor starts to get energized. And you know that we have already discussed this concept in AC to DC converters. So the inductor starts to store the energy, and capacitor starts to get charged, and we get the voltage at the output. Because of the switch, after turning on the switch, the battery gets connected to this load through this switch, through inductor, and so on. And we get a current flowing through this load. We get the output, V equal to IR. Okay, so mathematically, we need to find out that it is working in continuous conduction mode. So let's start with the voltage at inductor. So voltage at inductor is the, as we calculate it using KVL, Kirchhoff's voltage law. So supply voltage minus output voltage is the voltage drop at the inductor, assuming switches are ideal in nature. So no voltage drop at the switch, which is equal to L di by dt. And DIL is the current flowing through the inductor. L DIL by dt is the voltage in the inductor. So rearranging this L DIL by dt in this form, this DIL by dt we can represent in small deltas, very small change in inductor current with respect to very small change in time. So this one can be represented in terms of change in the inductor current with respect to change in the time, which is D multiplied by T. So delta T is same as D multiplied by T. So now we are assuming delta equal to D. And this time is equal to the total time period, one time period. And this delta, every delta means every D time, which is turn on time divided by T. So D multiplied by T is the total turn on time. So assuming the total turn on time as the delta, so how much change in inductor current happens in the turn on time period over here? That is equal to, because we have already turned it on. We have turned on the switch. And during this turned on time, which is equal to dt, how much voltage is developed across the inductor during this turn on time, which is equal to d multiplied by t, as we saw in the previous slides, which is equal to Vs minus Vo divided by L. So for the total turn on time of the switch S high, this is the voltage across the load, voltage across the inductor. So rearranging it further, total change in inductor current when the switch is on, which is also called close. So when the switch is on, what is the total change in inductor current? We get Vs minus Vo divided by L multiplied by d into t, this one. So just rearranging this. So this will be the total change in inductor current when we have turned on the switch. Now the second condition, when the switch is open. So now this circuit, this battery will be out of the circuit now, disconnected from the circuit because of the opening of the switch. So now this circuit remains. This switch, which is a diode in a simplified circuit, it starts to work because now the inductor will change its polarity and it will start flowing the current backwards. So it will start releasing the stored energy in the first case. So in this case, the total energy stored over here now getting released through this circuit, through this diode, and this current continues to flow over here through this load in same direction. So now what is the value of voltage over here? It is now, because the inductor reverses its polarity when it starts to release its energy. We have already discussed in AC to DC converters. During charging, it has a polarity, and while releasing that charge or releasing that energy, it reverses its polarity, and now it starts to flow the current in this circuit, which is equal to minus Vo, reversing polarity, which is equal to L by dt, this voltage in inductor. Again, using this delta IL by delta T. Now in this case, the turn off time of this switch is 1 minus dt. We saw that in previous case. Dt is the turn on time, 1 minus dt is the turn off time. So change in inductor current per turn off time will be minus Vo by L. So what will be the total change in current when the switch is off? Equal to this voltage multiplied by this turn off time. Okay, so we have already discussed that in part 2 of this course, that the net change in inductor current over one period is 0. We have already seen that the inductor current, whatever it has stored during the positive half cycle or during the switch on, it has to be released during switch off. So the net change is 0. So it means when the switch was closed, whatever was stored is completely released when the switch gets open. So that's why the sum of them will be 0. Whatever is stored is released. Already discussed in part 2 of the course. So now using these equations for delta IL closed over here and delta IL open, so using these two equations equating to 0, we get output voltage equal to the supply voltage multiplied by the duty cycle. And we know that duty cycle is always less than 1 or 100%, less than 100%. So turn on time of a switch is always less than 100%. It has to be turned off also, as you can see from here. So this is 50% of the duty cycle, less than 100. 75% of the duty cycle, less than 100. 25% less than. So the duty cycle is always less than 100. So here we can see that it is always less than 1. So output voltage is always less than Vs. because D is always less than 1. So that's why we can say from here that this is a step down converter where output voltage is always less than 1, always less than supply voltage Vs. Okay, so this output voltage is a kind of similar to the term we used in AC to DC converter as VDC. So VDC was a, what about the RMS voltage? Why RMS voltage? Because we have ripples, we have continuous current, and this continuous current charges, discharges, and it has the ripples. And due to these ripples, we have this average and RMS current. If the ripples are very small, depending upon the application. So again, the same thing, supply voltage square, taking mean from 0 to T on, turn on time, divided by the total time period, because turn off time, the switch is off. And then taking the square root, we get root D multiplied by Vs. So here it was D multiplied by Vs. RMS is a little bit higher value, root D multiplied by Vs. So in that case, these two formulas you have to remember. For buck converter, output voltage is always less than the supply voltage over here. Now, further analysis we have to do for further calculations. So now, again, as we have assumed that this current is continuous. And we also know that the average inductor current must be same as the average inductor current in load resistor, because both are in series. And in series, the current must be same. Load and inductor are in series, so the current has to be same. So the average capacitor current must be 0 in steady state condition. We are talking about steady state. So in that case, the inductor current equal to the load current, because of both are in series, which is equal to output voltage divided by resistance, the resistance in load. Now, to find out the maximum and minimum values of inductor current, we have to calculate these to find out what is the maximum and minimum, so that we can calculate the amount of ripple. And based on the calculation of ripple, we can decide further that how much filter or how much capacitance should be connected at the output. So all these calculations have to be done before we go for the final design. So what is the maximum value of current in inductor? This is IL, which is the average current over here, average inductor current in steady state, plus the delta, as we can see from here, because it is continuous current, charging, discharging, or means energizing of the inductor, de-energizing of the inductor, energizing again. So here the inductor gets energized at dt, which means the switch is on. From 0 to dt, the switch is on, and from dt to t, the switch is off. So I maximum is this peak over here, which is IL, which is the average current, we can see from here, divided plus this delta, which is delta IL divided by 2, because of this half of this. Now what is delta IL? We have already calculated in previous one. Use that value of delta IL, we can get this value of I max, which is 1 by R plus 1 minus D divided by 2ILF. Similarly, for minimum inductor current, which is this negative peak over here, average IL, average inductor current, minus this negative peak will give us the minimum value of current. So minus of delta IL, again using that value of delta IL, substituting that delta IL over here, we can find out the value of I minimum over here. And then based on this I max and I minimum, we can find out the value of L. From here, this L can be found out. So So from here, we have already found out the value of I max, the value of I minimum, and the value of L. So the minimum value of inductor current must be positive, because we never want to go to zero or in negative. If we see that the minimum value of current is not positive, it means we do not have a continuous flow of current or continuous mode of conduction. So it is a kind of a discontinuous mode or a boundary condition of continuous and discontinuous. So I minimum also has to be above zero. So minimum value of current has to be above zero. So this, based on this I max and I minimum value, we can calculate the value of inductance. So by calculating the value of inductance, we can decide the value of maximum and minimum currents. So from here, you can decide that what value of inductance this continuous current conduction mode will be applicable. As we can see from here, to find out the minimum inductance required for the continuous current conduction mode. So using these equations over here, we can use this. This one over here for I minimum, what is the minimum value and what is the maximum value of current. Using these two conditions, we can find out the value of minimum inductance over here. So for minimum value, we can, using that previous equation, putting that to zero, we can find out the minimum value of this inductor, which is 1 minus d. So if this inductance goes below this value, the current will not be discontinuous. It shows that. So to maintain this current in continuous conduction mode, this is the minimum value of inductance required. So it means we have already designed the value of inductor for this buck converter to work in continuous current conduction mode. So this is the same continuous current in inductor, so which we have just calculated. This is how graphically it is shown over here. Okay. Now, after we have found out what is the minimum and maximum value of current and the value of inductance required, how to find out the voltage ripple. And we know that the variation in output voltage ripple is actually calculated using the voltage current relationship in a capacitor, because ripples are actually associated with the capacitor at the output. So the capacitor current must be equal to the difference between these two currents, inductor and resistance current, due to the current division rule. So, or KCL over here. So the capacitor current has to be the difference between inductor and this one over here. So this is the inductor current IL. It gets divided into IC and IR, which is the load current, as per Kirchhoff's current law. So using that concept, we have come up with the capacitor current over here. So now the capacitor current is positive when the capacitor is charging. We know that. And using that concept, we can find out the change in voltage. This one, delta V naught. So this voltage, change in voltage in the capacitor, we can find out, and this is the value over here. So change in charge divided by the capacitance. So from here we can easily find out peak to peak ripple voltage, which is change in the output voltage over here. And now thing is, again, we have already assumed that these components are ideal in nature. So the supply power is equal to the output power because all are ideal in nature. So the losses are zero in between. So the power input, power supplied is equal to the power at the output. So based on the previous slides, this is the ripple factor, which is the ratio of the RMS and the DC voltage at the output. And using the formulas which we have calculated previously, we can find out the value of ripple factor, which is 1 minus d divided by d square root. So it means the ripple factor has a dependency on the duty cycle. So by changing the duty cycle, we can change the ripple factor.